It's time for Fun with Math, and we are back talking today about polynomial functions and models. So we're going to start with a little bit of a review. We're going to start by talking about how to solve polynomial equations and then inequalities. So let's look at an example of this to kind of review it. So the first one, of course, is an equation here. So we want to solve this equation, x cubed plus 4x squared equal to 5x. So in general, to solve polynomial equations that have degree bigger than 2, so this is degree 3 right here because the highest power is 3, there usually has to be some sort of trick because we don't know the equivalent of like the quadratic formula for a cubic equation. So in this case, the trick is, you're gonna move over the 5x. So let's subtract, 5x from both sides. And when you do that, you're going to see that they all have an x in common. So minus 5x is equal to 0. And because they all have an x in common here, we can factor out that x. So we're going to pull out an x and play this little game, sort of what goes here plus what goes there minus what goes there. That's equal to 0. So these pluses and minus just correspond right here and here. And then, okay, so what times x is x cubed? Well, that should be an x squared. Then what goes here times x gives you 4x squared. Well, that should be a 4x. And what goes here times x is a 5x, and that's a 5. So we can actually pull out that x, and then we're left with a quadratic expression, which we can probably factor. So let's factor it. So it's going to be x plus or minus something, x plus or minus something, and it's going to be equal to 0. The somethings come from the number 5, and so there's only one way to factor 5 and 1, or we write 1 and 5. And we somehow have to use this 1 and 5, add or subtract it, to get this 4 here. And so it's a positive 4, so I think that's probably a plus, and that must be a minus. And you can multiply that out to check. So if you multiply it out, you'll see you get x squared plus 4x minus 5. So now what happens is we have three things that we're multiplying by. This, and that. And we're getting 0. So what we know is either x is equal to 0, the first thing 0, or the second thing is equal to 0, or the third thing is equal to 0. And the reason for this is the only way to get 0 when you're multiplying stuff together is one of these things has to be 0. And so here's our first answer for x. Our second answer, we have to add 1 to both sides here, and we get x equal 1. And our third answer, we have to subtract 5 from both sides, so we get x equal negative 5. So this equation, which we would call a cubic equation, because it's degree 3, has 3 answers, 0, 1, and negative 5. And in general, that's true. So if you give me sort of, let's say, a 5th degree equation, x to the 5th minus 2x cubed plus x is equal to 7, let's say, I may not know how to solve it, but I know because the degree of this equation is 5, that tells me that there's going to be 5 answers. 5 answers for x. And that's true for all polynomial equations. Depending on what the degree is, you're going to have exactly that number of answers. Okay, so let's go down here and talk about polynomial inequalities. So remember, to solve an inequality for a continuous function, in general, if you have some function f of x and it's continuous, the idea is actually pretty simple. You can think of the sort of x-axis as being a river, and you're trying to figure out for an inequality when is the function above or below the river. So suppose you're trying to figure out when f of x is bigger than 0. So the idea is you're going to go find when f of x is actually equal to 0. And if you find these x values where it's equal to 0, that's the only spots where it can cross the river. So suppose you find out that x is equal to negative 1 and 3. And so here's negative 1, and then here's 3. So that's where that function will cross the river. And that's the only place it can cross it because it's continuous. So then what we can do is we can just test points to the left. So we can pick some point over here to the left, figure out if it's positive or negative. So suppose it was positive. Well, if it's positive, then all the points to the left over here, when you plug it into this function, to be positive, because it can't dip below without crossing one of these bridges. And then you'll pick a point over here, and suppose you find out it's negative, and then, of course, all the points in between here, if you plug into the function, will have to be negative, because it can't go above, right, the x-axis unless, you cross one of these bridges. And, you plug a number over here, and suppose you find out it's, positive again. And so then all the numbers over here are positive. And so then we can just simply write down when it's positive, it's all this stuff and all this stuff. And so we just write down that interval, and that's our answer. So let's look at this polynomial inequality. Just for fun, I can tell you what the degree is. Here, that has degree 1. This actually has degree 2. So this gives you degree 2. And then, of course, this has just degree 1. So altogether, you actually get degree 4. So this is a quartic inequality, if you want. Okay, so let's talk about how we're going to do this. So we know this is actually a continuous function. And so we want to basically find the zeros. So the first step to solving this inequality is simply finding the zeros and so of this, if you think about of the function if you want. And so when is it equal to 0? Now what's nice about this one is that it's already been factored for us. So again, we have these three things, this times that. And so we know either 7x is equal to 0, or x minus 2 is equal to 0, or I guess that's squared. So x minus 2 quantity squared is equal to 0, or x plus 5 is equal to 0. And so we're going to get three answers. If you divide by 7, this tells me x is just equal to 0, so there's 1, 0. If you take the square root of both sides, you just get x minus 2 is equal to plus or minus square root of 0, but that's just 0. Then we add 2 to both sides, we get x equal 2. And here we subtract 5 from both sides, so we get x equal negative 5. So these are like our bridges on our river. So we want to draw our sign diagram. So over here, let me block this off, where I guess I'll do it right below it here. So here's my sign diagram. There's my river. I know the zeros. I basically know the bridges in a sense. So I know it's 0 at negative 5. It's 0 at 0, and it's 0 at 2. And I want to plug in values to the left, to the right, and in between. So I'm going to pick test values here, so like negative 6. And I don't put that on my number line because I'll get confused if I do. Easy number between negative 5 and 0, like negative 1. Easy number between 0 and 2, like 1. And an easy number to the right of 2, like 3. And I'm going to plug it into this expression here. So I'm going to copy it. I like to copy it down right here. So I'm going to plug it into 7x, x minus 2, quantity squared, and then an x plus 5. And what we want to know is whether it's going to be positive or negative. So when you plug negative 6 in here, that's 7 times negative 6, so it's going to be negative 42. This is going to be negative 8 squared, so negative 8, and it's going to be squared. And this is going to be negative 6 plus 5, which is negative 1. Now remember, I don't care about the actual value. I just care whether it's positive or negative. So this square is going to make this positive. That's negative, and that's negative, so it's just going to be a positive. So I really don't need to multiply it out, because the only information I want is whether it's positive or negative. Now I'll do the same thing with negative 1. So for negative 1, you have 7 times negative 1, which is just a negative 7. And then I have negative 1 minus 2 squared, which is negative 3 squared, which is actually just 9. And then I have negative 1 plus 5, which is a 4. And so I have a negative times positive stuff, so this must be negative. And then I have a 1. I'm going to plug that in. That's going to give me a 7. And then times, it's negative 1 minus 2 is negative 1, but you're going to square it, so you're just going to get a 1. And then here, 1 plus 5 is 6. So that's positive. And then I'm going to plug in 3. If you plug in 3, that's a 21. And then 3 minus 2 is, and you're squaring it, is 1 squared, so that's just a 1. And then 3 plus 5 is 8. And so again, these are all positive, so when you multiply together, you get a positive number. All right, now I want to know when it's negative. I want to know when it's less than or equal to 0. So for my answer here, I'm going to look for when it's less than or equal to 0. So when it's negative, because that's what this says, right? Less than or equal to 0. So it looks like it's negative in between here. And then it's equal to 0 here and here. And then also right there. So how do we write this down? So we write it down like this. Negative 5 to 0, including the endpoints and all numbers in between. And then union, and this one's a little bit tricky, so I wanted to do this one on the video here. You write curly bracket, because remember, this is really a set with curly brackets, but we write an interval notation. And then you just put the number 2 in there, in curly bracket. Right? What I meant by that is, remember, over here, if you think about what does negative 5 comma 0 really mean, this is actually equal to the set of all x such that, that line means such that there, such that negative 5 is less than or equal to x is less than or equal to 0. It's less than or equal because of the closed bracket there, and then closed parenthesis. So remember, interval notation is just a shorthand for this sort of set notation, which we were kind of holding off on for a while, but you'll learn it a little bit later, but not in pre-calculus. All right, so this is my answer right here. Now, what's nice about these problems is, you do have to show your work, but you can always check your work. We can check our work simply by graphing it on a graphing calculator to see if it actually, is right. So on here, I'm going to turn this on, and I'm going to hit y equals, and I can graph this thing. So I can think about this instead of an inequality, it's just like a function. So 7x, oops, let's go to y equals, and hit 7x, and then left parenthesis, x minus 2, and then square it, and then left parenthesis, x plus 5. So there is that expression written as in here as a function, and then I guess on my window, I'm just going negative 10 to 10, negative 10 to 10, and then I hit graph, and let's just see what happens. So we can see if we can see where the zeros actually occur. Right? So I don't think this is a very good graph. So one thing, I'm going to go back here. This looks fine. I think my window needs to be changed a little bit. So when something like this happens, it's not a very good picture. So what I'm thinking I'm going to need to do is I need to force my graph to kind of look at it a little bit closer. So I think what I'll do is, I know where the zeros occur. So I'm going to look a little bit to the left of this 0, so like negative 6. I'm going to look a little bit to the right of this 0 here, so positive 3. And I don't know what the output should be, so what I'm going to do is I'm going to go to zoom. And there's a button on here called zoom fit. And what it does is it fits the output to the inputs that you gave. So here's zoom fit is 0. I'm going to hit enter on it and see if that doesn't give me a little bit of a better picture. There we go. Oh, much better. All right, much better. Okay, so I can actually tell you kind of what's happening here. So it's definitely negative at negative 5 to 0. And then it's going up a little bit, but it's going up such a little bit. I'm kind of zoomed out kind of far. You can't see it, but it's going up a little bit and then coming down and probably touching here right at 2. And then it's going to flip and go back up. So you can see from the graph that, yeah, it's negative only from here to here. Otherwise, it's going to be above the x-axis, and it's going to hit 0 right there at 2. So it checks, basically. It's a nice way to check if you can get the graph to work right. But sometimes you can't. Sometimes it's hard to get that graph to work right. So that's how we solve polynomial inequalities. All right, so let's talk a little bit about what are polynomial functions. So this is what they kind of look like, and it looks really complicated, but it's actually not that hard. So the idea is it's just you have some coefficients here. These are just coefficients, and we use these sort of subscripts to denote them because there could be lots of coefficients. So for example, we could have f of x equals 2x to the 5th minus, 4x to the 4th plus 2x cubed minus 3. I'm going to skip some here, so I might say 3x plus 7. So that's an example of a polynomial. Polynomials, there's some numbers that are actually very important. So we talked a little bit about this when solving equations and inequalities. This number, this is the biggest power. It is called the degree. And it gives us some nice information about the polynomial. In particular, like if you want to find a number of zeros, it'll tell us there's basically 5 zeros. Now remember, not all those zeros may be real. You may have some imaginary zeros, basically. So, but you know there's at least five zeros, basically. There's 5 solutions to equate this function if you set it equal to 0. We'll come back and we'll talk more about this in a little bit. But let's look at an example involving a table first, and we'll come back to it. All right, so here, this is a table, and we want to kind of work with this table, and we want to try to figure out, determine the type of polynomial function. Is it linear? All right, so remember, linear would look like something like this. We'll use mx plus b, like y equals mx plus b. It has basically degree 1. Or is it quadratic? So we looked at this, last time, and this was y equals, and we can write this as ax squared plus bx plus c. And of course, the degree for this is 2. And then cubic looks like this. It has degree 3, so it's like ax cubed plus bx squared plus cx plus d. And finally, we have quartic, and that should not be quantic, it should be quintic. All right, but quartic looks like this. It has ax to the, instead of cubed, is to the 4th. The power, or the degree, is 4. Plus bx cubed, and then hopefully you'll let me get away with this. Just write dot, dot, dot. It goes on, and then you get plus d. And same thing with the quintic, except it has degree 5, so it goes ax to the 5th plus bx to the 4th plus dot, dot, dot plus d. And after that, we quit naming them because, you have degree 6 polynomials, degree 7 polynomials, degree 8, and so on and so forth. But we want to determine what type this is. Is it linear, quadratic, cubic, quartic, or quintic? And the way that you could do this is just how you kind of determine when a function's a linear function with a table. So the idea with the table, if you look at a linear function, so let me make one for you here. So like x and y, I'll make something 0, so make something easy. So we'll start 0, 1, 2, 3. And over here I'll put 4, and let's put 7, and let's put 10, and let's put 13. So I know this table is modeled by a linear function because when you take the differences here, you always get the number 3. Right? So the differences here is 3. So it has what we say is, it's constant rate of change. And then we talked about quadratic functions when we look at their tables, and we saw that quadratic functions, they don't have a constant rate of change, they have a linear rate of change. And so you don't take the difference just once, you take it twice and you see it's constant. So it's a linear rate of change. And then you can kind of build off this. Linear functions have constant rate of change. Quadratic functions have linear rate of change. Then cubic functions will have quadratic rate of change. And they'll just keep going on and on. So they kind of build off of each other, which I think is nice to see. So quadratic, oops, I forgot the rate of change. All right, so let's look at this example. So if you take the difference here, and you always take the final minus the initial, so 2 minus 5 will give you negative 3. And then you take the difference here, 21 minus 2, that'll be 19. 74 minus 21 should give you 53. And then 173 minus 74 should give you 99. And 330 minus 173 should give you 157. And you can do this with your calculator. I already did these, so I'm just copying them down from paper here. But you can do them on your calculator. And you can see that the rates of change here, they're not constant. So I immediately know it's not linear. And so then I'm going to do this again. Because if they're constant when I do it this time, then I know it's quadratic. So you take 19 minus a negative 3. So remember, minus and minus is a plus, so it's actually 22. 53 minus 19 should give you 34. 99 minus 53 should give you 46. And then finally, 157 minus 99 should give you 58. And again, you say, oh, these are not all the same. So now I know it's not quadratic. It doesn't have linear rate of change. But you do it one more time, And if we do this one more time, what you're going to notice is that the difference between each of these numbers is 12. So the difference between 58 and 46 is 12. And so what that means is that this table has what we could say a quadratic rate of change. And so that basically tells me that it's going to be a cubic function. All right, so what type of polynomial will you use to model this table? What will fit the data? It's going to be a cubic function over here. Now a good question is, how do you find that formula? Right? So how do you find the formula? Now we're not going to do this right now. We actually do this at the very end of the semester because we need to know a little bit about what are called determinants in solving systems of equations. But I can tell you the idea. So how do you find the formula? It's actually very simple. If you know the type of formula, and you just got to figure out what A, B, C, and D are, well, you have information over here. You know if you plug in 0, you get out 5. So let's plug in 0 for x. So that's going to be 0, 0, 0, and you just get out D, and of course the output is 5. So y is 5, and you get a bunch of zeros, and you get a D. And so you really know this piece of information here tells us that D has to be 5. We still don't know what A, B, and C are, but we have more information. So what happens when you plug in 1? It says you get out 2. So 2 should be equal to when you plug in 1. So if you plug in 1 for x, you get 1, 1, 1, and so it's just A plus B plus C plus D. So you have A plus B plus C plus D. Still don't know what A, B, C are, but I do know what D is because it tells me right here. But you can get more information. So here, if you plug in 2, it tells you it's 21. So I know 21 is equal to, when you plug in 2, now 2 cubed is 8, so I get 8a, plus 2 squared right here is 4, so 4b, plus, and then you plug 2 into here and you get 2c, and then plus a d. And if you notice, you keep on doing this, but you can stop after the next one. So you do one more. If you plug in 3, you get 74. And so I get 74 for the output. And then the input, I plugged in 3. So 3 cubed is 27. So I have 27 A's. Plus 3 squared here, you get 9 B's. And then plus, you plug in 3 here, you get 3 C's, plus a D. And that's all the information you really need. So to solve for 4 unknowns, you typically need 4 equations. So I have 4 equations. And then there's a way to figure out what A, B, C, and D are, which we'll learn at the end of the semester. And so then you'll be able to see that this is actually y equals 2x cubed plus 5x squared minus 10x and then plus 5. And so that's the formula for this table. So if you plug in the number 5 here, if you plug in 5, if you do 2 times 5 cubed, you can do this on your calculator if you want, plus 5 times 5 squared minus a 10 times 5, and then plus a 5, your calculator will tell you it's 330. Which is kind of nice. You know, if you know the table's cubic, you can actually find the formula. And that's really one of the goals in this class, right? One of the goals is, you know, you have a table, you have a graph, and you have a formula. These are the 3 different representations of a function. And really what we're trying to do is just be able to go back and forth in between each one. So if you give a table, can you find a graph? If a graph and a formula, or vice versa, a graph of a table, a formula or table, or you know, here, if you have a formula, can you make a table? If you have a table, can you come up with a formula? Right? We like to go back and forth between these 3 representations. That's really our goal with each type of function. And sometimes we can, and sometimes we can't. It really depends upon the type of function we're working with. All right, so let's get off of there, and let's actually go back. I'm going to go back to where we were before, because I want to talk a little bit more about these formulas. All right, so if you're given a formula, like last time we talked about this one, this 2x to the 5th minus 4x to the 4th plus 2x cubed minus 3x plus 7, there are some important parts to this. So the most important part to a polynomial is called the leading term. And the leading term is the term with the biggest degree, with the highest power, basically, right? So this 2x to the 5th is the leading term. So that's just the leading term of the polynomial. It's the one with the biggest power. And then the leading term has what's called a leading coefficient. And so in this example, the leading coefficient is just the number 2. So this is the leading coefficient. And it actually tells us some important information about the function, which we'll talk about in a minute. So that's the leading coefficient. And of course, we have the degree, which we already talked about. I did that in red, so let's just circle that in red. And the degree is the power on the leading term here. So, and that's the degree. It's just the biggest power in the polynomial. All right. And then we also have something called end behavior, and we'll talk about that in a minute. But really, the idea is like, what happens to this polynomial in the end? Does it go all the way up, or does it go all the way down? Right? Or then you can look on the right-hand side, or you actually go on the left-hand side and say again, does it go all the way up, or does it go all the way down? So I'll talk more about that, but this is really what we mean by end behavior. And it's not that hard to understand once you get it, but it's just like what happens to the polynomial in the end. Let's look at an example, and I think that'll clear things up for us a little bit. So here's the example we want to do. Now, when I wrote this polynomial out, when I gave you this polynomial, I didn't multiply it all out because I didn't want you to multiply it all out, but you can multiply this all out, and it can be written in this, sort of form, a n x to the n plus, a sub n minus 1 x to the n minus 1, and blah, dot, 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 down to some, constant, a sub 0. But I didn't want to multiply it out because that's actually the easy problem. It's a little bit harder if you don't. And so I want to do kind of the harder problem here. So first, we want to classify the polynomial as linear, quadratic, cubic, or quartic. So the idea is it degree 1, degree 2, degree 3, or degree 4. And so we have to use our imagination a little bit and think about what might happen if you multiply this out. So the 1/8 doesn't give you any degree because it's just a number. But this thing right here, this x minus 2, it's being cubed. So remember, if you multiplied that out, what it would mean is you take x minus 2 times x minus 2 times x minus 2. So eventually, when you multiply this out, you can think about the first term. I don't know what the other terms are, but I know the first term is going to be an x cubed plus a bunch of other stuff, which I don't really want to figure out. But I know there's going to be an x cubed. So just as I'm looking at this, I know this is going to give me an x cubed. And then over here, you have an x. And so if you take x cubed times x, you're going to get, in the end, when you multiply this out, there's going to be some x to the 4th over here. And I don't know what the number is right now, and I don't know what's going to be after it. I have no idea. But I know there's going to be an x to the 4th, so that tells me it's going to be quartic. So you just kind of look at the x's and the powers here, and you can use that to figure out, what x to what power is going to wind up when you multiply it all out. All right, so it's going to be a quartic. That's the type of polynomial. And then the leading coefficient. So what's the leading coefficient going to be? Now be careful, it's not the leading term, it's the leading coefficient, so it's the number. So we're trying to figure out what number is going to go here when you multiply this all out. So notice this, if you take x and x minus 2 and you cube it, you just get a 1. There's no number in front of the x cubed. And same thing here, x plus 3, there's going to be no number in front of the x term when you multiply it out. So the coefficient just comes from the 1/8 because you're going to multiply everything by 1/8. So that's going to be 1/8 x to the 4th plus a bunch of other things, who knows what. So my leading coefficient is actually 1/8. And then, let's make that 8 better. And then finally, our leading term here, which I've already written down. So the leading term, what is it going to be? It's just going to be this whole thing. 1/8 x to the 4th. So 1/8 x to the 4th. So you got to use your imagination a little bit. You really don't want to multiply it out if you don't have to, although sometimes I notice if I do this type of problem on an exam, you guys just multiply it out, but you're not really supposed to multiply it out because it's more work than you really have to do. But if you want to check your work, I guess, and you have time, you can do that. Okay, so now which choice represents end behavior of the given polynomial? All right, so end behavior, there are a couple ways you can do this. We're going to talk in a little bit about limits, not today, but later. End behavior is just what happens to the end of this graph. So you can say stuff like, what happens as you take the limit as x goes to infinity of this function. And that would be what happens as you go all the way to the right over here. And you can tell me what that equals. And then you can look, instead of going all the way to the right, you can go all the way to the left, negative infinity of f of x, and tell me what that is going to do. Now, because the leading term is this, when you plug in really big numbers, you just get out really big numbers, and they're positive. So this is going to be infinity, basically. And if you plug in negative numbers, because it's the fourth power, if you raise something to an even power, it's going to make it positive. So this is also going to be positive infinity. So you plug in really big negative numbers, it'll also be really big, but no longer negative. So you can see, if you go to the right, if you think about this, if you go to the right here, it's going to wind up here. If you go to the left, it's also going to wind up here. And so my answer would be A. So that's how I think about it. Now I could also just use my graphing calculator, right? So let's just use our graphing calculator, because there's nothing here. It's not about showing your work. It's just about understanding the question. And so here, if you wanted to, you're also allowed to use your graphing calculator. So here you could do 1 divided by 8. And then do left parenthesis x minus 2. And then raise it to the 3. So raise it to the 3. And then kick it out. And then do x plus 3. End parenthesis. And now for our window, we're going to do a standard window, so because it says here negative 10 to 10, negative 10 to 10. So when I zoom this, I'm going to go down to zoom standard. Instead of doing it by hand, you can just see standard. I'll do a negative 10 by 10 window so you can see what it kind of looks like. So there's what it looks like right there. All right, so you can see that on the ends, I'm going to go to the left, it ends up, and you go on the right, it ends up. So my end behavior looks like A. It's not B, it's not going down on both sides. It's not C, it's not going down on the left, up on the right. It's not D, it's not going up on the left or down on the right. It has to be A from the picture. And now we want to graph this. Right? So when we graph this, I expect you to use your graphing calculator to help you. And then you know the window because it tells you right here, look from negative 10 to 10, negative 10 to 10. And you just want to trace the graph the best that you can. I think you probably should get these zeros on here because you can kind of see where the zeros are. There's a 0 at 2 and negative 3. So let's put that on there. So there's going to be a 0 here at negative 3, because if you plug in negative 3, that'll be 0. And there's going to be a 0 at 2 right here. And then we may even want to find the Y-intercept. So usually the rule I use for you guys is if you're going to graph it, you better find the X and Y-intercepts if you can. And so to find the Y-intercept, that's when you plug in 0. So if you plug in 0 here, you're going to get 1/8. And then if you plug in 0, that's going to be negative 2 cubed, which is actually just 8. So times 8. And then plus a, oh, it's not positive 8 though. Be careful, it's negative 8, right? Because it's negative 2 cubed. And then plus 5, times 5, sorry. Look at this plus. So I'm plugging in 2 plus 3, and so that's a 5. So times 5. And so these 8's cancel, and then you get negative times 5, so just negative 5. So it also passes through negative 5 here. And you just want to try to connect the dots the best that you can, mimicking what you see here. You know, so right here, it looks like it just kind of goes concave down. So let's connect those dots in a concave down manner, like that. And then it changes and goes concave up. So let's do something like that. And look at the graph again. Oh, it actually has a minimum down here. Now, I don't know where that minimum is, and I don't expect you to know where it is. If you really wanted to, you could trace this thing and get an idea. But I really don't need that kind of precision. But somewhere like negative 2/8. So, you know, I can put it down there somewhere, like right around here. But I don't know it exactly. And, you know, it goes up like this. And then over here, it's going to go up and continue to go up. If I miss my point that I'm going through, I just draw the point a little bit bigger, right? But it looks something like that. That's good enough, I think, for the overall picture, because we're just kind of sketching the graph. All right, so let's move on, and let's talk about modeling. And so modeling with polynomials it's kind of fun because now we get to do volume, basically, right? So we did perimeter, we've done area, and now we get to do volume. So remember, volume, to find volume of a rectangular box, is just length times width times height. So here we want to express the volume of the figure shown as a function of x, and then determine the possible values of x if the volume of the figure is 1,855 cubic inches. And they give us the picture, which is nice. And we know the volume. The volume of this thing is supposed to be 1,855 inches cubed. And we want to find x. And so how do we how do we do that? So the problem with this picture, or the problem with this figure, is it's not a perfect rectangular box. It's kind of like a little rectangular box with another little rectangular box cut out of it. And that's exactly how we're going to solve this, actually. So what we're going to do is we're going to look at this and define the volume, define the formula for the volume of this blue rectangular figure. What we're going to do is we're going to find the volume of a rectangular box, and let me outline it for you. So hopefully you can see there's a big box with a little box cut out. So here's the big box right here. We're going to find the volume of that box. So volume of blue figure will be volume of red box, basically. And then we're going to take away, and then we'll take away, there's a little box right here that we're going to take out of the red box. And that's going to give us the volume. If you see that green box, we'll take the volume of that away, and that will give us the volume of the blue box. All right, so this is the whole idea that the sum of the whole, the whole is the sum of its parts, basically, right? So the whole is the red, and the red is the blue plus the green. So to find the blue, you take the red minus the green. So let's just do that. So how do we find the volume of the red box? Well, it's just length times width times height. And so you got to kind of look for the height here, and the height's listed over here. So you just got to move it over. That's okay. You just put it right here. So that's x plus 5. And so it's going to be this times that. And so the volume of the red box is 5x plus 3 times x plus 2, and then times x plus 5. And you'll notice that's a cubic polynomial, and it should be because volume is cubed. And then we're going to take away the volume of the green box. Now for the volume of the green box, again, you have to think a little bit, kind of rearrange the picture, use some spatial reasoning here. So this is x, and then this length here they didn't write down directly for you, but it's right below it. It's just x plus 2. It's the same as this length right here. And then this height, they didn't write back here, but they wrote up in front, it's just height 3. And so it's going to be x times x plus 2 times 3. So the length times the width times the height. So it's going to be x times x plus 2, and then times 3. Right? And then that's a formula. Right? That's the formula for the volume of the blue box right here. And you can simplify it if you want to, but you don't have to. You can leave it just like that because it doesn't actually say, find the formula. It says find x. Right? So that's what we're actually looking for. Now find x when the volume is 1,855, and maybe I should have put that volume in blue, because that's not the volume of the red box, that's the volume of the blue figure given to us in the picture below. And so what we're going to do is we're going to take that volume and we're going to plug it into here, and we're going to solve the equation. So we have 1,855, and that should be equal to, we write down our formula there, 5x plus 3 times x plus 2, and then times x plus 5. Minus, and I'm going to put that 3 in front. I just like to put the numbers in front. So 3x times x plus 2. Now, how are we going to solve this equation? There are a number of ways to solve it. You could multiply it all out, move all the numbers over to one side, and see if you couldn't figure out what the answer is. And you might have to guess and check, to be honest with you. But there's an easier way to do it with your technology. And so that's the way we're going to do it. We're going to solve any equation that's probably bigger than degree 2 with some sort of technology. So to solve it with technology, we've done this before, but the idea is we're going to graph the right-hand side of the equation, and then graph the left-hand side of the equation, and then we'll intersect. So if you haven't done this, follow along with me. You can pause the video if you get stuck or lost and rewind it if you like. So what we'll do is we'll just graph the right. So plug in the formula on the right. So left parenthesis, we have 5x plus 3 in parenthesis, left parenthesis, x plus 2, and then left parenthesis, x plus 5, in parenthesis, and then minus, we have 3x, and then left parenthesis, x plus 2. So there's the formula. And so when we graph that, we're going to get a graph that's graphing that formula. But we're also going to graph the left-hand side. We're going to graph the 1,855. And what we'll find is that there's going to be two graphs, and we're going to find where they cross. Now, the hard part of this is where are we going to look? So hit the window button, because we have to set up the window. And so we have to figure out what x might be. We have to think about what x might be, basically. And if you look at the picture, here, this is 3 and this is x, and they don't look very different. So I would guess, I always start at 0, but I would guess that x is not going to be much bigger than 3. So I might go from 0 to, let's just do 0 to 10 and see what happens. So 0 to 10, I do not know what the outputs are necessarily going to be, so I'm going to hit zoom and do zoom fit. So remember what that does, it fits the outputs to the given inputs we put in. So just hit enter on zoom fit, and let's see what kind of graph we get. So this is the graph of the formula on the right, and then we should see the 1,855 come across, and then where they meet is the answer for x. So let's copy this down. So when you do the solution, I do like you to show some work. So I require you just to copy down the graph that we saw and write down where you looked from 0 to 10. And we just copy down the graph like this and copy down like this. And what you're going to do is you're going to use a button called intersect. So I always tell you just write down that one big button idea that you used. So intersect. And so where you find intersect is if you look behind the trace button, there's a calculate button. So you can hit second, trace, and that pulls up the calculate menu. These are all different things we can do with the calculate menu, which we've seen before. We've been finding, I think, maximums, most recently, and we found zeros one day. But now we're going to go down here and just do this intersect. And so we hit enter on intersect, first curve, second curve, give it a guess, and it pops right to it. So 1,855. So my answer, of course, is that x equals 5. So my answer is x equals 5, and not 5 just anything, it's 5 inches. So that's important, so don't forget the units. So 5 inches.